All right. Welcome to the second seminar. This year, Liliana Apolinario is gonna now go into current research, I suppose. And since I've done an introduction already last time, let me just say we're very happy to have you back and continue this two-part seminar. Now let's see how far you dare to go in this pretty tricky business. Take it away.
Thank you. So as previously, please feel free to interrupt me whenever you want. So on this for this section, I just before kicking in the latest works that I personally have been involved. Let me just make a brief overview of what we discussed in the last seminar. So as I showed you, so jets in heavy ions are pretty much different from jets in PP, in proton-proton, or what we call as in vacuum, simply because there's a multitude of processes going to happen during the parton shower evolution that will come out as a different jet. So in principle, we will have both energy loss via medium-induced radiation or via collisional processes in the medium that will turn out afterwards as a sort of wake that we usually call the medium recoil. So this is the component of the medium particles that are excited through the interactions with the jet and will then thermalize eventually also with the medium, but will leave some sort of wake. And the problem of having all these processes here is that not only our jet is different, but also the description that we try to employ for these methods needs to be chosen very carefully, as the energy scale at which this happen is usually towards the non-perturbative region, especially for the parts of the medium recoil effects. Now, we know that there is jet quenching because we already saw the effects of having quark-gluon plasma in there. So one of the most immediate consequences is the fact that our jets will have less energy with respect to a vacuum. And this is, for instance, one of the events that we see in which we have indeed the dye jet that we would see in the absence of a quark-gluon plasma. Now, one of them is very much quenched with respect to the other one, reflecting then the presence of a quark-gluon plasma. And this is what we call by energy loss. So the energy is basically redistributed for the rest of the event. And so because of the complexity of the jets, we always focus on the building blocks. And this is exactly the same approach as between proton-proton. We start with the building blocks. And in the seminar, I will focus essentially on the most, let's say, basic of the QCD building blocks, which is the gluon-Bremsstrahlung. We basically showed in the last talk how exactly we go from basically addressing QCD Bremsstrahlung from vacuum in medium. There are several assumptions that we need to build. First, we need to start with our characterization of the quark-gluon plasma, which basically we put as a collection of quasi-particles with a given screen potential, such as Yukawa. So something that it's actually also employed in nuclear physics. And then we try to compute basically the cross-section of this process, what we call the medium-induced gluon radiation spectrum, which is basically computed via the calculation of the amplitude times the complex conjugate. And from there, we can have some sort of diagrammatic representation of exactly what is the medium, the gluon energy spectrum that we acquired. And as I also basically told you in the last seminar, the big challenge of putting ourselves into this sort of calculation is exactly to understand how to calculate the emission kernel. So all the medium information comes in this dipole cross-section that appears both in the emission kernel, that is the part of the spectrum that is proportional to the formation time of the gluon system. So basically the difference between the longitudinal coordinates that are within our amplitudes. And this dipole cross-section has here exactly the building block or the basic assumption, let's say, that we do on the medium characteristics, which is the parton-medium interaction potential that, as I told you, can be some sort of Yukawa screen potential. And the problem that we currently have when addressing this is because since we do need to make some sort of assumptions here to actually solve this emission kernel, the current status of which we can withdraw or compare our numerical or our analytical results with data is not exactly the most precise one. So we have some sort of a landscape of this Q hat parameter that is basically connected to the dipole cross-section, that is also the interaction potential, which is parameter that comes often when we do the dipole approximation in our interaction potential. This is the two approximations that we talked in the last seminar. So we have the opacity expansion, that in which we basically expand our spectrum in terms of a number of interactions with the medium, or we simply say that we resum over all scatterings, but we simply accommodate like small momentum transfer exchange with the medium. And so the current status of what we can do or what we can extract with current RHIC and LHC data, I mean, it's not something that it's completely nonsense, but still it can be improved. And it can be improved by going higher in accuracy on how to describe exactly this building block. And so basically there are two major, let's say, different approximations that will come out very recently to actually try to solve and go beyond the approximations that we usually employed to describe this path integral, which is the kernel, the emission kernel. One of them is actually to, instead of having an opacity expansion that is in the number of scattering centers, people decided to say that, okay, if in the dipole approximation I can resum over all scattering centers, then I can try to be more accurate in the way I do this expansion around the harmonica, the dipole approximation. So in this set of papers, what people came out is that they do an expansion, but around exactly the dipole approximation. So they again resum overall scattering centers, but they go a little bit higher in accuracy to say that I don't not only transfer small momentums, but also perturbations, additional perturbations around these small momentum transfers. And this is one way to solve or to go higher in accuracy to the emission, to the radiation spectrum. So, but at the end of the day, we always need to compute something that is numerical, because we have integrals that might not be, and in fact, they are not able to be performed analytically. And so instead, what me and collaborators decided to do was, okay, let's try a different approach. That is to say, since we employ numerical methods already, we can start to employ it earlier in the calculation, and in that regard, just includes all the limits in our calculation. And so just briefly to basically show exactly what each one of these approaches is doing is basically the improved opacity expansion is exactly what I was telling you, which is an expansion around the harmonic approximation. So this is the emission kernel. This is the usual equation, the usual evolution equation. And what they do is exactly to expand, to shift a little bit the point around which they expand the solution. And so you can think of the solution that you come out with it is simply the harmonic oscillation plus a correction that now you included also in your results. And this is kind of a series in the same series of opacity expansion, but opacity expansion again is just to truncate the series in terms of number of scatterings. Here I truncate the series in terms of transfer momentum between the QGP and the probe. In our case, what we do is, okay, let's go back again to the first emission kernel that to the first expression, the analytical expression that we have from considering gluon radiation. And again, don't forget that this K here with the tilde is the emission kernel, where is the path integral, and the most difficult, the most challenge bit of this calculation. And then we have the broadening. And so what we do is that we first basically rewrite the spectrum in a different way. As you can see here, we go to momentum space and not coordinate space as we used to do in this kind of calculations. And then we start by integrating analytically one of the integrals that are here and just already subtracting the vacuum contribution, because the spectrum itself, when we calculate the medium-induced radiation in the gluon, we always have two contributions. The contribution that is perfectly in which the gluon is emitted within the medium, but since we consider usually finite size effects, we also have the possibility that the gluon is actually emitted outside of the medium, just the quark itself propagated through the QGP. And so we subtract, and when we do this, we have three terms, and one of them is the pure vacuum contribution that we simply remove. This is also standard, but the fact that we do it here at this level analytically allow us to now write this expression and have now the broadening perfectly identified with a given partial differential equation that will give the evolution of the broadening. And the same for the kernel, okay? This is just analytical calculations. If you want the details, I can share with you, but these are just simple analytical exercises. They seem too fancy, but it's just this. And so this means that now we have a set of partial differentiating equations that can be solved analytically. And we just need the initial conditions for these differential equations. Once we have the initial conditions, we can evolve both the broadening and the emission kernel up to the scale in which we are considering for the rest of the spectrum and do all the integrations. Okay, so this is just numerics from the beginning to the end. And of course, the initial conditions are very simple in this case. The initial conditions for the broadening is that it didn't broaden, and for the emission kernel, there was also energy momentum conservation, and that's it. And so with this, we have just to basically code a simple code to solve our spectrum, and we can do the spectrum for any kind of potential or any kind of settings that we want. Well, in fact, when you go to the paper, and this is just for you to basically, when we open the paper, don't be scared about the notation, because the point is that we don't actually use the broadening and the emission kernel directly, but some version of it, because it's simple for our analytical solution. So basically, these objects are just the same or are proportional to exactly the broadening and the emission kernel. And so with these settings, now we can compare with the previous assumptions that people used to do. So let's start with the GLV, the first order opacity. And so what we have here is our results. This is what we call the full Yukawa for using the potential that is the Yukawa one. And as you can see, we have some sort of parameters here, but just to demystify a little bit. So as medium parameters, we have the initial density, which in our case, we will consider to be fixed for the moment. We have the medium length, and we have the bi-screening length, which is a characteristics also of the medium. And then we plot the emission spectrum in as a function of the energy of the gluon. This kappa here is just the transverse momentum scaled by the Debye mass, but still we call it transverse momentum. And this x is just the inverse, it's just the energy, which we plot here as the inverse of x, just because of the numbers are easy to plot. So the first observation is that indeed, when we go to higher energies, so smaller x, my spectrum is much less present than when we have smaller energies. And this goes in the same direction as vacuum. As I mentioned, this kind of gluon radiation calculations are usually done in the soft limit. So we always consider the gluon to be the softest particles and the one that can go some sort of random motion in the transverse plane. The quark is just allowed to exchange some finite, some color fields, and it's kept fixed in the same transverse position. So it doesn't change any kind of momentum with the gluon. And in fact, we assume that this is the case, and the result that we have actually tell us that as well, that the corrections that are coming from considering a gluon with finite energies are small. And so this is something that we already knew from, for instance, using a GLV approximation. What we didn't knew was actually, or what we didn't got so right, was the magnitude of the gluon radiation. So GLV over accounts the gluon radiation when compared exactly to the full solution. So, but in terms of features, we see that there's no significant features. So the features of the spectrum are the same. They are very much different from vacuum radiation. In vacuum radiation, we would expect something that goes as 1 over k squared, which in this case is not the case. So again, we have, of course, that it's very difficult to emit a gluon with a high transverse momentum. But if we consider a soft, because we have kind of a color field that is generated by the quark gluon plasma, my spectrum is not divergent. My spectrum is finite. And this is what we see exactly here. So, and of course, the tails of this distribution are very much accurate in the GLV, because this is the region where they actually target. But for the soft momentum gluons that are generated via typically multiple gluon emissions, this part of the spectrum, of course, is not so well described by the GLV. But with our method, we can actually have a very good now description of this part of the spectrum. This, of course, is for dilute medium, which is again the region where. Yeah.
Maybe a silly question. Are we considering a constant by streaming?
Yes.
Okay.
Yes. In this kind of in this process, yes. And at the end, I will show you exactly how we could or how we managed to incorporate actually a variable, also the biomass, to accommodate also the medium expansion. But for the moment, this is fixed. And so this is for the dilute, the region where the GLV, of course, it's targeting, because if you have few scatterings with the medium, then in principle, we are considering the medium to be very much diluted. Of course, that if you go for a more dense set of parameters, in which here of course, we have a combination always of these 3 parameters in a different way. And so we usually fine tune through this in the N0L. And so if I choose these values to be higher, then as you can see, of course, the spectrum is much more suppressed in the real case, while now we have a very strong difference between the full solution and, of course, the GLV, because the GLV now is completely out of its validity region, because we are considering only the first order in the opacity. Of course, that if we could consider, or if we for this comparison, if we would consider higher orders in the GLV approximation, then of course the spectrum would be more similar to this one. But since we are considering only n equals to 1, we know that this is not the region of validity of this model, and this is just to illustrate exactly how much difference is with respect to the full solution. Now we can do exactly the same thing for the energy spectrum, because so far we focused only on the double differential gluon radiation. So we have both the information of the energy and the transverse momentum, but from the point of view of the jet itself, and this is exactly what we use, for instance, to withdraw the transport coefficient, we need to integrate over the transverse momentum. And when we do that, we have to impose here the constraint that the transverse momentum, of course, cannot be larger than the energy. And so the energy spectrum now that we get here is usually emitted as the preferred, more or less, what we call the characteristic energy, which is related basically to the medium parameters. And again, the features are basically almost the same. So we have the spectrum that peaks at the characteristic angle, and then we have some sort of, let's say, quotient spread up to higher or lower energies. But again, the magnitude between the GLV, which is in dash, and our full solution, now it's very much different. Of course, this is more important the larger the medium is. While if I have a very short medium, as you can see, even though in the previous plot I show you that there is some differences, especially in the low region, the low momentum region, the truth is that for the jet energy loss, this mismatch is not so important. This mismatch comes exactly from having a difference between the angle, between the gluons that are emitted at the typical energy that is related to the characteristics of the QGP. And as you can see here, for instance, so if I go for instance, 5 Fermi, and this is more or less the order of magnitude that we would expect from the LHC, something between 5 to 10 Fermi, we see here that we have indeed a very much different prediction of the energy spectrum, and this of course will reproduce a different amount of energy loss. So this means that when we extract the Q hats, I get different values of Q hats depending on the models that I'm using in my jet analysis. And now I can do also the same with the harmonic oscillator. The harmonic oscillator, don't take it exactly very much an apples to apples comparison, because the harmonic oscillator, in fact, we have 2 medium parameters, while in the full calculation we usually use 3. So we have kind of a freedom to actually match these 3 parameters to these two. And so I'm not exactly analyzing the magnitude of the spectrum, but more on the shape, okay? Because I have some freedom here to fine tune this. But still, I can now do the same for the double differential spectrum and for the energy spectrum. And of course, that's, again, we have more or less sensible shapes, because this is the most dominating region of the medium parameters that I'm now including here. But we see that, for instance, these tails here that reflect the high momentum transverse, and for instance, this part here that is the gluons that are emitted with a very large angle are pretty much failed in the harmonic oscillator regime. So again, this part of the spectrum will reflect, again, a different Q hat parameter. And so this is basically to show you in which sense we are migrating from something that is less accurate to something that is more accurate. And one of the good things to have now a spectrum that can fully resum over all scattering centers without making any kind of approximation is that now I can try different, for instance, potentials for the quark-gluon plasma. So I can just focus on some sort of Yukawa, which is basically static scattering centers, or I can even refine now the description of my quark-gluon plasma and instead considering the interactions in a thermal plasma as basically the QGP would be. And for instance, in this kind of plot here, I have now in solid the full Yukawa predictions, and in dash the potential that comes from hard thermal loop calculations. And in this case, the bimass that we used is considering 3 flavor quarks that are behaving as free particles in the quark-gluon plasma, which again is more or less the same what we would expect from LHC collision. So at that temperature, we would expect just the 3 lightest quarks to participate in this kind of interactions. And again, we do some matching between this kind of potentials with the parameters to exactly reflect the same kind of medium parameters, the average medium parameters. And as you can see, now we are becoming more sensitive to the nature of the quark-gluon plasma, which before we couldn't, because we were convoluting basically the nature of the quark-gluon plasma that we are using with the model that we are also employing for the interactions with the medium. From this moment on, we have now the possibility to actually explore different potentials and see if they have indeed any consequence on our jet phenomenology. Unfortunately, this part of the work is still much ongoing. We didn't actually, also due to lack of human resources on our side, we couldn't explore exactly the consequences of having different potentials for jet analysis. So at the level of phenomenological analysis, what this means. But at least we know that we have sensitivity. Now it's just a question of understanding if this will have an effect or not in the experimental results. And this is again Of course, this is for the light dilute medium. Of course, that if we go for very dense mediums, the differences now start to be a little bit more mild. And of course, we don't expect to see much differences in the extracted Q heads. But for instance, the region in which the medium is already diluting or at RHIC energies, perhaps we can have some sensitivity to actually say if the quark-gluon plasma is better described by one form of the potential or the other. In principle, we would expect this to be more correct actually than the Yukawa. Okay, so with this, let me now show you what we can do. Now that we basically surpassed the difficulty of evaluating path integrals, now we can try to actually go for other missing things that we know that there are in these jet quenching calculations. And for instance, one of them is that in these kind of calculations, you notice that we always consider the particle to be produced at the very beginning of the medium. So we always put the particle, the initial quark, to be to start to propagating at time 0, and at time 0 there is already a QGP. But we know that this is not the case. I mean, after the hard scattering, the fields that are generated by the collision are very, very strong, and they will need to thermalize eventually in the quark-gluon plasma. And the interactions that we assume as static scattering centers can only be applied actually in this state of the quark-gluon plasma. So there is this part here, the pre-QGP phase, that we actually don't know how to module. And so the question arises, do we have some sensitivity to this part of the QGP? Can we use jets to actually try to probe this particular time frame of the collision? And in our current calculations, we cannot do it because we assume that this is not the case. But the point is that if we try now to have some sort of shift in this part of the spectrum, and we try to fit the RAA, people have done this, and they don't find any kind of sensitivity. And this is actually quite expected, simply because if we basically consider a shorter medium, we simply need to retune the Q head to actually describe the experimental data. So it's true that the value of Q head, by considering a shorter medium that instead of starting at 0 starts later, will impact on the absolute value of Q heads. But still, since this is our fitting parameter, we can still fit the data. But what people realize is that even though we don't see any kind of effect in the energy loss, this is no longer true for the flow coefficients. So the flow coefficients, especially in peripheral collisions, so this is the overlap region that you produce when we have the two nuclei not completely overlapped, there will be some modulation of flow. This is what we also discussed in the last seminar, which actually is a signature of fluid-like behavior for the quark-gluon plasma. But we also have a flow from the jet itself, because the jet is very high energy, and so it will induce some asymmetry also in the event. And so I can correlate basically not only the soft particles of my event, but I can correlate the highest particles, which are coming from the jet, with the low event, with the low momentum particles of the event. And so this is what they call the V2 SP, which is just the correlation between the soft and the hard modes of your collision. And so in principle, while this part of the spectrum of the V2 here is described by flow, by usual like hydrodynamic models, because this is exactly the part that comes from the QGP itself, the high momentum flow should be correlated with the jet. And what people have discovered is that in order to describe this high momentum V2 of the events, that is again comes from the jets, I actually need to delay the quenching with respect to what we would assume by more or less 0.5, 0.6 Fermi. And this number actually is fairly consistent across the different models. So we have some sort of puzzle, because from the point of view of the jets, we say that there is no quenching before the QGP. Now, if we consider carefully, this cannot be the case, because we have a very strong electromagnetic fields there. So there should be something that we are clearly not understanding. But this indicates a problem in our calculations. We cannot simply consider a shift also to kind of do this exercise. So in this exercise, they indeed consider just a different, a delay in the quenching when the particle starts to interact with the medium. And this, of course, is necessary to preserve more this high V2, because if I leave the particle within the medium, this high V2 will basically thermalize, and there will be time for thermalization to happen. And of course, I decrease now the magnitude of the V2. But this situation is no longer physics. It's no longer a physical realization. What we should instead be considering is exactly this kind of setup, in which if I assume that I have some vacuum propagation, then I should allow also the possibility that the gluon is emitted within this time frame, within this pre-KGP phase, and only afterwards will start to enter with the medium. That is to say, I'm usually, in the previous calculation, I consider finite size effects at the final stage of my evolution, of my quark-gluon system evolution, but I should also consider exactly the same kind of finite size effects at the beginning, if indeed I have some sort of transition between the pre-QGP phase and the QGP phase. And so, of course, that in this part of the exercise, we assume vacuum propagation. Now, this is, of course, no longer the case, because we know that there are strong fields, so it shouldn't be vacuum propagation. Because we don't know how exactly to modulate that, we basically just wanted to check the effects of adding interferences that are coming from a pre-QGP phase in our calculation. And this was the only purpose of having exactly this thing. So this means now that I include this vacuum propagation here. I include also the possibilities that I have radiation also in this part. And of course, I include the interferences that come exactly from considering the different possibilities in my radiation part. And so this is exactly the result that I have when I look now for the energy spectrum. As I told you, the energy spectrum is the most important thing if we want to retrieve the Q hat. And as you can see, the colors are basically connected to this figure. And of course, that if I consider a shorter medium, I of course radiate less, so my energy spectrum will be smaller. But this part here actually depletes a little bit the energy loss as well, because now I have vacuum, but it's not exactly compatible with this one either. So the truth is somewhere basically in the middle here. And of course, this is also seen when we use, for instance, harmonic oscillator approximation as well. Of course, the difference between these two scenarios are not so strong in the energy loss, which you also saw in the RAA, because in this paper here, they use harmonic oscillator approximation. Indeed, the energy spectrum is very much equivalent to one another, but if we now try to look for the elliptic flow, things will be different. Now, to do this exercise with our calculation, again, we use the quenching weights. So the quenching weights are just the prefactor that we include in the factorization scale that I show you when withdrawing the Q hat from analytical calculation. So this is one of the possibilities. And so because we have here the quenching weights, I can simply calculate the quenching factor as basically the ratio between the cross section when I have this quenching weight as being 1 or vacuum, or when I have this quenching weight as being the quenching weight that takes into account that I have now a medium-induced gluon radiation. And so I can now make several assumptions for the cross section of the proton-proton or from the vacuum. We know from purely experimental observations that usually the spectrum goes as 1 over pt up to the 6 or up to the 5 or something along these lines, depending on the square root of the energy that you are considering, or if you are also talking about particles or jets. So these are just basically have different slopes. But in any case, it goes as 1 over pt up to the some power. And so we can use this information to actually now calculate the quenching factor using this shift here. And so we have now from our analytical calculation just a proxy for the energy loss, which would be like a nuclear modification factor. And this amounts to calculate basically the suppression that we have, for instance, in some peripheral events here between what we call the in-medium plane and outgoing plane, because since the path lengths are different, I have to average over all possible paths to get an average energy loss, and that's why we basically sum both these contributions and divide it by 2. But this is exactly the kind of measurement that we want to do if we want to look for the V2, because the V2, since these are the correlations with the jet, if my jet comes here, then this part here is dominated by the soft particles, and this means that I have a measurement of the correlation between the high and the soft particles of my event. And so this allows this quenching factor allows to have some sort of measurements or proxy for the V2. It's not exactly the same, but people have proved that this is fairly suitable for this comparison. And so we try to exactly check what would be the effect, again, on the energy loss or on the V2. And as you can see, the amount of flow that survives when I do this kind of approximation is again radically different from this thing here. So this means that, again, if we want to compare exactly the V2 and the RAA on top of each other, as we previously did in the past, we actually need to consider exactly these interferences, because these interferences will have a very sizable effect on the V2 itself. So we cannot simply say that, yeah, there seems to be no quenching in the initial stages of the collision, because if we indeed consider no quenching in the pre-KGP phase, the V2 that we have is not compatible with what people were thinking. It's much more suppressed. Okay, so again, this is just to make like a call of attention to the fact that, yes, we have some problem also describing the pre-KGP phase. Again, this is not realistic because we don't have...
Where does this sizable effect come from? I have a hard time coming up with a reason why this would be big.
Yes. So in this situation, it's big because since we are effectively saying that we have a shorter medium with respect to what we would have. So if I have a shorter medium, this means that I don't have time to actually thermalize all the energy of the gluon within the medium.
Okay.
And so I have a higher V2.
But
now,
where is the thermalization effect coming from if you do this? Well, the calculation right before you hit the red, it's vacuum situations, right?
Yeah, this includes the vacuum propagation before the QGP phase.
So there's something happening with vacuum vertices, but why would that be? Right, I mean, you're bringing down, nothing happens quite a bit
Yes.
with purely vacuum behavior. Yes. Because you don't know how to include anything more complicated. I'm not blaming you for that, but why is this effect so big?
Yes. The point is that the fact that we are including some sort, because we are not including just vacuum propagation, we are including also the interferences with the medium. So if we were to include only vacuum propagations, the effect would be not so drastic. You're right.
Okay.
But because we have the interference with the medium contributions, and these medium contributions are known to suppress quite much the flow, because
this is an interference effect between amplitude and
exactly.
Yeah. Okay.
Okay. Exactly.
Okay. I'm there.
So, and that's the point. So the driving effect of this is not exactly to include some vacuum propagation, it's actually the interferences that come from these states with the diagram in which the gluon is emitted in this case.
Thank you. That was very useful.
And of course, that's if we hopefully in the future would have a better modulation for this vacuum, then this would help us very much to understand exactly what is happening here. Yes. So finally, the last piece that I wanted to show you in basically the advantage now of having something that is more accurate with respect to the previous case is actually the effect of medium dilution effects. So usually what we say is that, okay, we have here the density of the scattering centers that we assume in our calculation. And now I say, well, it's not so difficult to actually include here some sort of temporal evolution of the density of the scattering centers. And from that moment, my calculation now starts to be valid regardless of whether I have a central production point in a peripheral collision or not. So with some sort of time dependent the density of scattering centers, I can imagine that, okay, now I have some collisions. I have some information from the hydrodynamic profile that is generated within the collision.
Pardon me, I'm making a nuisance out of myself. There is also the Yukawa, right?
Yes.
The biomass in the game.
Exactly.
Shouldn't you also adjust this in concert?
Yes, when we change the density, we also change the biomass in the same way.
Okay, good. Thank you.
And so now what actually says or dictates how this density, and by construction in our case, the biomass as how it evolves, is actually now the hydrodynamic profile that is generated for the QGP. And for instance, here, I'm plotting basically the kind of trajectories or kind of in medium path lengths that the particle would follow as a function of time for different, for instance, hydrodynamic, for the same hydrodynamic model, but for different initial conditions. So this is assuming a Glauber model, and this is assuming a different set of initialization conditions for my hydrodynamic profile. And this is, for instance, some sort of trajectories. And as you can see, now I'm not fixed to one average trajectory. I can do this event by event. But this comes with a price. And the price is that, this is exactly what you were asking me, is that now my density and the biomass, even though they are a function of the medium temperature, of course they are allowed to have different scaling parameters. So we need to fine-tune this for every kind of trajectory, because we actually don't know this mapping. And so we have this problem, and we have an additional problem, that is to actually generate the spectrum for a single trajectory is something that it's not exactly instantaneous. So this is the price of paying of using a full numerical solution very early in our calculation. Now it will take more time with respect to some analytical methods. And so for jet phenomenology, this is something that is quite impractical to do it on some sort of, for instance, grab this, put in a Monte Carlo, and hopefully to generate a full parton shower with this kind of results. And so this is actually a problem that was known for the community, and what people thought is that, okay, now instead of having exactly an event by event, I would probably suffice for energy loss purposes, not exactly for the jet substructure. For the jet substructure, this is completely not applicable. But for the purpose of evaluating the jet energy loss, I probably suffice to say that I have an average trajectory with a given analytical dependence of my density and of my the biomass. What people used before was some sort of average, more or less values, constant values. What we instead propose to use is actually something that is a little bit more refined and takes into account exactly the kind of evolution that you see here. And when we try to fit this, we come out with an expression that is pretty much a power law dependence that is more or less well reflected with a linear dependence for the mu square, and of course the NT goes with 0.5. And so now with this kind of assumption for my medium evolution, I can of course compute the equivalent of a static scenario would be what would be actually to just use what we call a brick of QGP, which is just a rectangle, which was what I showed you before. And of course, I want now to compare this with the realistic events and say, okay, what I'm exactly missing if I'm not computing this event by event with a real hydro profile in the case in which I consider the medium evolution without any kind of assumptions. And so what we present here is basically the comparison between the three settings. That is to say, the at pink is the hydro, which would be the full solution, no assumptions, and no attempt to actually simplify the medium evolution. So this would be a realistic event that is diluting with time. And this would be our, let's say, our parameterization of the evolution. And this is the static case, which is the brick, okay? And as you can see, for the energy loss, we simply need to, in order to have a more accurate description, we actually don't need to run this on an event-by-event basis. We can simply use a kind of dilute medium parametric form. That's basically this was the best solution that we came up, and instead calculate basically the spectrum for this solution. And then when we try to use an event-by-event simulation, we simply calculate the equivalent of these parameters, and we can simply tabulate basically the spectrum for a given set of n0s, t0s, and simply read in these numbers. So this avoids this heavy calculation of the spectrum at every time that I want to run some sort of jet energy loss analysis. So instead, I pre-compute this. I have some sort of a table that I simply input in my codes, and I simply read the parameters that account for the hydrodynamic profile that I'm about to use. And what we showed is that this is valid for very central collisions in which I have a very well behaved evolution. But it also amounts to say that, okay, of course, that the precision at which we can do this for more strange configurations of in medium production points, such as this one, in which my particles produce more on a peripheral region, but traveling towards the beginning, towards the center of the collision. Of course, the temperature will now have this kind of shape because it will increase because I'm going to the denser region, and then decreasing because my medium is evolving, and I'm also traveling outside of the collision center. And of course here I'm now starting to have some sort of differences in the energy loss that I extract, but still are much more alleviated with respect to what we would have by considering a static scenario. And so as my summary, I just want to highlight that we now have several attempts to go beyond what we used to have as being the multiple soft, which is the dipole approximation, or the single heart, which would be the GLV expansion. But don't forget that we are still limited to soft gluon radiation. So our calculations are intrinsically assuming that my gluon is soft. So it's true that I try to extrapolate this to the low modes of the energy spectrum, but we know that in that region in particular, we are of course incurring some not so precision results. The advantage of using a full numerical solution is that for the first time we seem to have some sensitivity to different interaction potentials that we can now test it. We also have some sensitivity to the pre-QGP phase with this simultaneous analysis of the V2 and the REA, and the better understanding exactly what is going on in there. As you also asked, I mean, it's not exactly the most important thing, but this comes from the interference of having something that is not the QGP as we depicted and the QGP itself. And of course, we now can consider the medium dilution effect. So, and this of course amounts to say that by incorporating all these effects, we can now go to a very much precise quantification of hopefully the QGP characteristics. All these are not yet implemented in the Monte Carlo, but at least at this building block of the shower, this is basically the current status of the art with this kind of approach. Let's say. And yeah, that was basically what I wanted to show you. Thank you.
Thank you very much. That was to the force. You guys have moved quite a bit on from when I last paid attention to this. So this is actually quite interesting that you can get this far numerically. I'll open for questions in a second, but I have to ask my own first. This is pushing it a little bit. You have a debye mass in there. This is your only infrared regulator in the game. Is that true?
Yeah.
So if you check your integrals, you're not running into long distance physics anywhere. I assume that you've done this just to verify.
Yeah.
And it's enough to do. So presence of the debye mass on this level is enough to keep this infrared safe.
Yes.
So,
yes. But
okay.
yeah, but I understand your concern. Yes, that's also my concern. Exactly. How dependent are we?
Yeah, I mean, right. If you were trying to do I don't know a sketch type factorization ansatz of sorts, right? If you try to push for that, you have to unearth the debye mass first, right? In order to get to something that looks like what you're doing, and that doesn't look like a trivial exercise.
Yes. Yes.
Right.
I mean,
Or,
in our case, we simply say that I mean, these parameters are chosen so as to reproduce more or less what we know that is the average energy loss that comes from our current data from LHC. But we are not sure exactly how to control exactly these divergences. You're completely.
I mean, hot thermal loops, of course, suggest that there is a debye mass.
Yes.
There. So this is the QCD side of the calculation in a way, but then how to do a factorization properly on top of this is not totally trivial.
No, I agree.
All right. So now that I've gotten rid of my question thing, are there any more questions?
I had a question, but just following up on what Herbert said. I know some people use like a magnetic dipole. Is that because I saw because you've got the 1 over q squared and then a q squared plus mu squared. And I know I've seen some people suggest from lattice and stuff that there's the presence. It's not with an HDL, but
yeah. Well, this
should be a magnetic.
This is one step. It's even one step further.
Right.
This is genuinely.
But is this the same issue you talked about?
It's a similar issue. You need something to regulate the inverted. Otherwise this sort of calculation cannot be done.
But that's all. I mean, that's a parameter you can put in. It's not a real.
Well, no.
At the moment.
But in principle, right? But in principle, there is reason to expect that it's there.
Yeah.
Yep.
But the really original question.
Yes. My original. Yeah. Well, let me just ask one. But so this thing is going to take alpha value here. It was interesting to me that you fit a value of alpha as 0.5. I kind of thought, like from something like the Yorkian expansion, I would have thought it should be 1 maybe, but is this, yeah.
Yeah, so we actually tried, that was our first guess, to have an alpha equals to 1. And basically, from the moment that we have 0.501, there are some differences here when we do the ratio with respect to the full solution. But at least for the range in which we tried 0.5, I think it's overall it yields better results with respect to alpha equals to 1. And I think that the driving mechanism behind this is actually because since we also assume the biomass to go more or less as linear as the density, which, I mean, I'm not sure exactly if this is the case or not, we basically come out with 0.5. So I wouldn't say that 0.5 is to say that we are not having a Bjorken-like expansion. It's just the fact that we are making these ansatz. So we have to basically say that the debye mass and the debye mass goes linearly as well as the expansion of the medium. But it might not be the case.
Do we have more questions? Well, I've had mine during the talk.
Well, I think there's no other questions. I have one other question.
Should.
Near the start, there was a step when you were kind of doing more analytics, where you went from an energy loss kernel, which I've seen and I understand, to like a partial differential set of equations, which I didn't understand how that happened.
You mean these ones?
Yeah. So where did the differential equations come from?
Sorry?
The one that you use for the numerical.
Yeah.
What I'm guessing.
Yes, this is the one that we use for the numerics.
So how do you get the differential equation, or is it? Yeah.
Well, the differential equation that you have from here is simply by inspection. So here, what you do is basically to expand the broadening by one little step, for instance, and saying that the broadening comes from the first interaction and then the rest. This is like some sort of, I'm not sure if you ever had this kind of Schwinger-Dyson type equations for the low part of the QCD. They use exactly the same kind of formalism in which they expand the propagator and they basically, yeah. So this is basically the same. So what we did was to expand this one step in the opacity, one step in the opacity, this one, and then from there we can simply rewrite this as an evolution equation for the broadening and from the kernel.
No more questions? Well, in that case, let's say thank you again.
Thank you.
Thank you for two very energetic talks. And let me turn off the recording now.